Dear students, today we will learn limits and continuity. Already I have learnt limits in our first video class and continuity in our second year class. So today we will discuss problems on limits and continuity. Before we go to problems, let me discuss some of the synopsis of this topic, or let us recall whatever that we have learnt already. Let f of x be any function. Then we say that limit of f of x as x approaches a, which is denoted by this limit of f of x as x approaches a. We say that it is equal to L, where L is a finite quantity. We say that it is equal to L, provided when x approaches a, whether it is from left side or from right side, whenever x approaches a, if f of x approaches the same quantity L, then we say that limit of f of x as x approaches a is equal to L. Okay. Let me take one example. I think earlier also in my first class on continuity I had taken the same example. Let me define f of x is equal to x square minus 1 divided by x minus 1. Okay. Now I would like to see what is the value of limit of f of x as x approaches 1. What happens to this? Limit extends to 1, f of x is equal to what? Let us observe. For this, it's better if you draw the graph of this function. Observe this function. What is the domain of this function? Domain of this function is the set of all reals except x equal to 1. At x equal to 1, this function is not defined. So the domain is set of all reals except 1. Because at 1, the denominator becomes 0, or it will become 0 by 0, an indeterminate form. So at 0, this function is at 1, this function is not defined. Everywhere else it is defined. So the domain is r minus 1. Now I want to know what happens at x equal to 1, whether the limit exists or not. That we should check. If you draw the graph of this function, at x equal to 0, f of x is equal to 1. At x equal to 1, it is not defined. At x equal to 2, put x equal to 2, we get 4 minus 1, 3 divided by 2 minus 1, which is 1, 3 by 1, 3. At x equal to 2, at x equal to 2, the function will reach, f of x will be equal to 3. At 3, it will be equal to 4, because when I put x as 3, 9 minus 1, 8, divided by 3 minus 1, 2. 8 by 2, we get 4. Then if I put x as minus 1, then what happens? It will be 0. Numerator is 0, denominator is minus 2. 0 by minus 2 is 0. So at minus 1, it is 0. So if I draw the graph of this function, that graph looks like this. Okay, it's a straight line. But with a break at x equal to 1. At x equal to 1, the function is not defined. Okay? At x equal to 1, the function is not defined. This is 1 here, this is 2, 3, 4, etc. At 1, the function is not defined. Okay. Now you look at the graph. When x approaches 1 from left side, when I say x approaches 1 from left side, that means x is very close to 1 but less than 1. Then what happens to f of x? This is the graph of f of x. F of x is very close to 2. And when x approaches 1 from right side, that is x is approaching 1 from right side means x is very close to 1 but greater than 1. There in that region, f of x is approaching 2. So whether x approaches 1 from left side or from right side, f of x approaches the same quantity. Then we say that limit of f of x as x approaches 1 is equal to 2. Limit extends to 1, f of x is equal to 2. Okay. So from this we observe that for the existence of the limit, it is not that necessary that the function to be defined at that point. Even if the function is not defined at that point, then also limit may exist. Okay. See, for the existence of the limit, we need to check only two things. One is the left hand limit and the other one is the right hand limit. Check whether those two exist or not. Left hand limit and right hand limit, do they exist or not? That is what we have to see. If they do exist, after that whether they are equal or not, that we must observe. Okay, if the left hand limit and the right hand limit both exist, and if they are equal, left hand limit is equal to right hand limit, then we say that the limit exists. The function has a limit at that point. Okay, so now I said for a function, for the existence of the limit, it's not all that necessary that the function to be defined at that point. Even we have seen, even when the function is not defined at that point, then also limit may exist. Okay, and on the other hand, if the function is defined, then also there is no guarantee that the limit to exist. For example, let me take a look at f of x is equal to step x. I will take f of x is equal to step x. Step x, as we know, the greatest integer less than or equal to x. And I would like to see what happens to limit extends to 2 f of x, which means limit extends to 2 step x. This I would like to see. What is the value of this limit? You just observe the graph of step x. I think this is well known to you. These two functions, the greatest integer function and the modulus function, these are two very important functions which we are going to use everywhere, especially in values. Okay. So from 0 to 1, step x is equal to 0. At 1 it will be 1. From 1 to 2 it is 1. At 2 it is equal to 2. From 2 to 3 it is 2. From 3 to 4 it is 3 in this way. This is the graph of step x. Now we observe, I want to find out what is the limit of f of x as x approaches to. First I find out left hand limit. Left hand limit is denoted by limit extends to 2 minus f of x. When I write extends to 2 minus, don't think that x is approaching minus 2. It is not. It means that x is approaching 2 from left side. When x approaches 2 from left side, means x is in the left neighborhood of 2. Okay, left neighborhood means very close to 2 but less than 2. Okay, so I'll explain that neighborhood afterwards. Limit extends to 2 minus f of x means x is very close to 2 but less than 2. So when x is very close to 2 but less than 2 means x may take the values 1.8, 1.9, 1.95, 1.99, 1.99999, etc. It's very close to 2 but less than 2. At all those points, what happens to step x? Step x, as we know, at x equal to 2, it is 2. When x is less than 2, when x is between 1 and 2, step x value is equal to 1. So this value will be equal to 1. However, right hand limit is equal to limit extends to 2 plus f of x. That's equal to limit extends to 2 plus f of x, which is step x. That's equal to x is approaching 2 plus means x is in the right neighborhood of 2. X is coming towards 2 from left side. See here, from right side. When x approaches 2 from left side, f of x is approaching 1. This value is 1. This is 2. When x approaches 2 from right side, f of x value is approaching 2. Because when I write x tends to 2 plus, its meaning is that x is very close to 2 but greater than 2, which means x may take the values 2.1, 2.05, 2.01, 2.001, etc. At all those points, step x value is equal to 2. Now we observe that left hand limit is equal to 1 and right hand limit is equal to 2. They are not equal, hence the limit does not exist. Okay. See, from these two examples, we observe that if a function is not defined at a particular point, then also limit may exist. And on the other hand, if the function is defined at a particular point, see here the function is defined everywhere. The domain of step x is the set of all real numbers. This function is defined everywhere. Even then, the limit may not exist. Okay. But I am not trying to tell you that when the function is not defined, then the limit exists, and when the function is defined, then the limit does not exist. That's not my point. My point is that when x approaches a, be it from left side or be it from right side, if f of x approaches the same quantity, then limit exists, irrespective of whether the function is defined at that point or not. Okay. And if the left hand limit is not equal to the right hand limit, then the limit, we say that the limit does not exist. Okay. Now I'll tell you what is the neighborhood of a point. Neighborhood of A. Okay. Let A be any point, let A be any real number. Then let delta be a very small positive real. Let delta be a very small positive real number. Then A minus delta, A plus delta. This delta should be sufficiently small when compared to A. This A minus delta, A plus delta. This is called the neighborhood of A. For example, say here is 2. So if I consider an interval like this, let me choose 1.9 or 2.1. I am saying that A is equal to 2 and delta is equal to 0.1. Delta is sufficiently small when compared to A. Okay. So 1.9, 2.1, that looks like A minus delta, A plus delta. This is called the neighborhood of A or the neighborhood of 2. It's not that delta should be equal to 0.1 only. You can take delta as 0.2 also. Then you will have 1.8, 2.2. Right? Again, this is also the neighborhood of A. Right? But don't choose A as 2 and delta as 100 and say the neighborhood of 2 is minus 98, 102. A minus delta, A plus. We don't call this as a neighborhood. The delta should be sufficiently small when compared to A. 0.1, 0.2 when compared to 2. They are much smaller, right? So, right. This is called the neighborhood of A. A minus delta, A plus delta. Let A be a real number. Then delta is a very small positive real number. Then A minus delta, A plus delta is called the neighborhood of A. Then in this A minus delta to A, this interval is called the left neighborhood of A. And A to A plus delta, this is called the right neighborhood of A. Left neighborhood of A, right neighborhood of A. Then if I write the A minus delta, A plus delta minus A. Again, from this interval, from this neighborhood of A, I am removing A. This is called the deleted neighborhood of A. Okay, deleted neighborhood of A. So here, this is the left neighborhood of A. This is the right neighborhood of A. Now, for the limit to exist, already I have mentioned that the left-hand limit must be equal to right-hand limit. While finding the left-hand limit at x equal to A, we choose this interval. We choose values for x in this interval. Then for right-hand limit, we choose values for x in this interval. See, earlier in one example, we have seen that even when the function is not defined at a particular point, then also limit can exist. We have seen that with the f of x equal to x square minus 1 divided by x minus 1 at x equal to 1, the limit does exist even though the function is not defined at x equal to 1. Okay. So, but even though it is not necessary for the function to be defined at a particular point for the existence of the limit, but it should be defined in the neighborhood of A, in the deleted neighborhood of A. It should be defined in the deleted neighborhood of A. See, that function x square minus 1 by x minus 1 is defined in this interval 0.9, 1.1 minus 1. If I consider this interval, there it is defined. Okay. So then these are the basic things which we already know. Now let us discuss some of the properties of limits. Let f of x and g of x be two functions where limit of f of x as x approaches A and limit of g of x as x approaches A both exist. Then we can write this. Limit extends to A, f of x plus or minus g of x is equal to limit extends to A, f of x plus or minus limit extends to A, g of x. Okay. Then limit extends to A, f of x into g of x. See, I want to apply the limit for the product of two functions. you can apply the limit for these two functions separately. Limit extends to a f of x into limit extends to a g of x. We can apply the limit separately and multiply. Okay. Similarly with sum and difference. Whenever you want to apply the limit for the sum of two functions or the difference of two functions, you can apply the limit separately and then add them or subtract them or multiply them. Or in case of division, limit extends to a f of x divided by g of x. This is equal to limit extends to a f of x divided by limit extends to a g of x. Provided this denominator should not be equal to 0. Provided limit extends to a g of x is not equal to 0. Provided this limit is not equal to 0. Limit extends to f of x by g of x is equal to limit extends to f of x divided by limit extends to a g of x. Provided this is not equal to 0. Okay. Then limit extends to a log f of x can be written as log of limit extends to a f of x, which means this log and limit can be interchanged. Then if I have limit extends to a f of x to the power n, we can write this as limit extends to a f of x whole power n. Okay. Then let us have a look at some of the standard results which we have already learned. Limit extends to a x power n minus a power n divided by x minus a. This is equal to n into a power n minus 1. This formula is well known to you. We have derived this in this class. Limit extends to a x power n minus a power n divided by x minus a is equal to n into a power n minus 1. From this I can write another formula, that is limit extends to a x power p minus a power p divided by x power q minus a power q. This is equal to p by q into a to the power p minus q. Okay. This is another formula which you need to remember. How do we get this? Let me derive this formula for you. Limit extends to a x power p minus a power p and divided by x minus divided by x power q minus a power q we have and divided by x minus a. Apply this formula separately. Say this will become, I can directly write that. Limit extends to a, think of this. Limit extends to a x power p minus a power p divided by x minus a. That is nothing but p into a to the power p minus 1. Then in the denominator, limit extends to a x power q minus a power q divided by x minus 1. That is equal to q into a to the power q minus 1. So a power p minus 1 divided by a power q minus 1, that will give you a power p minus 1 minus of q minus 1. 1 gets cancelled. So this is equal to p by q into a to the power p minus q. P by q into a power p minus q. Okay. Right? This formula you remember. Then the other formula what we have seen is limit extends to 0 sin x by x is equal to 1 and limit extends to 0 tan x by x, this is also equal to 1. Limit extends to 0 sin x by x is 1 and limit extends to 0 tan x by x is also equal to 1. Provided this x is in radians. If x is in radians, this is the formula we have to use. If x is in degrees, then also it is true, provided both should be in degrees. Limit extends to 0 sin x degree by x degree. This is also equal to 1. Similarly, limit x tends to 0, tan x degree by x degree is also equal to 1. But among these two, if one of them is in degrees and the other one is in radians, one of them is in degrees and the other one is in radians, then we cannot use this formula directly. Then what we have to do is convert either that radians into degrees or one of those degrees into radians. Make sure that either both are in degrees or both are in radians. Then limit x tends to 0, sin ax by x is equal to a. How do we get it? When we have sin ax here, we want ax in the denominator. So multiply and divide by a. Okay? Sin ax by ax as x approaches 0 will become 1. So that 1 into a will be equal to a. So then I can write that limit x tends to 0, sin ax divided by tan bx. This is equal to a by b. Because say here in the numerator we have sin ax. So I want ax in the denominator. I will multiply and divide by ax. Sin ax by ax into ax. Then here we have tan bx. So I want bx in the denominator. Bx into bx. As x approaches 0, this quantity will become 1. Sin ax by ax. Similarly, as x approaches 0, tan bx by bx will also become 1. X gets cancelled. So we will have a by b. Okay. So when we apply the limit here, in some cases, when you have, let us say, whenever if you directly apply the limit, we might end up getting some indeterminate forms. Indeterminate forms means 0 by 0, infinity by infinity, 0 power 0, 1 power infinity, 0 power infinity, infinity minus infinity, etc. These are all called indeterminate forms. Okay? Among them, if we end up getting 0 by 0 or infinity by infinity, when we directly apply the limit, let us say you have limit x tends to a, f of x divided by g of x. Okay? Let us assume that we have this problem. Here if I directly apply the limit, let us say that we are getting 0 by 0, which is an indeterminate form. Then we have one shortcut for this, that is called L-Hospital's rule. L-Hospital's rule, which says that when we directly apply the limit, if you are getting 0 by 0 or infinity by infinity, then this limit is equal to limit x tends to a, f dash of x divided by g dash of x. That is, you have to differentiate this and differentiate this separately, not by using quotient rule. You treat the numerator as a different function and denominator as a different function. Differentiate them separately. So f dash of x by g dash of x. Now you apply the limit. You will get the answer. If you get the answer, well and good. Even now, if you are getting 0 by 0 or infinity by infinity, then use this formula again. That is, differentiate this again. This is equal to limit x tends to a, f double dash of x divided by g double dash of x, which means I am differentiating. Derivative of f dash of x is f double dash of x, derivative of g dash of x is g double dash of x, and this process continues. Okay, till you get the answer, you can continue this, provided you have 0 by 0 or infinity by infinity form. Then only you can do that. I will give you some examples so that you will understand it better. So let me take very well-known examples only. Few examples. I will go by the actual method also, and then I will go by this. Suppose if I have limit x tends to 2, x square minus 5x plus 6 divided by x square minus 3x plus 2. Okay. So if I ask you to evaluate this limit, what do? You will evaluate, right? How do you evaluate? First we will check by directly applying the limit. See what happens. If I directly apply the limit, I am getting 2 square 4 minus 5 into 2 10 plus 6. 4 minus 10 plus 6. Numerator is 0. Denominator 4 minus 6 plus 2. 4 minus 6 plus 2. That will also give you 0. So this is of the form 0 by 0, an indeterminate form. Okay. First I will solve this by the actual method, then I will go for L hospitals. So in the actual method, what we will do, we will factorize it, right? So we will write it as limit x tends to 2. We will factorize this. On factorization, it will give you x minus 2 into x minus 3 divided by x minus 1 into x minus 2. On factorization, this is what we get, right? Now I cancel x minus 2, x minus 2. Then we get limit x tends to 2, x minus 3 divided by x minus 1. Apply the limit now. 2 minus 3, that is minus 1, divided by 2 minus 1 is 1. So the answer is minus 1. This is the actual method, which you have already learned in first PUC. Okay. Now that you know another formula here, L-Hospital's rule, let us say how we can make use of it. So here also, first you directly apply the limit and see what happens. When we directly apply the limit, we are going to get a 0 by 0. So I will use L-Hospital's rule. L-Hospital's rule suggests that it can be used. Remember, it can be used. It's a very useful result. It can be used only when you have 0 by 0 or infinity by infinity form. Okay. Other than that, you cannot use this. Okay. So here we have 0 by 0, so we can use it. How to use it? Differentiate the numerator and the denominator separately, not by using quotient rule. Separately you differentiate. So if I differentiate the numerator, I am getting 2x minus 5 divided by. If I differentiate this denominator, I am getting 2x minus 3. Now apply it. Put x as 2. 2 into 2, 4 minus 5 minus 1. Divided by 2 into 4 minus 3, 1 minus 1 by minus 1. Minus 1 by 1, we have minus 1. Here also we got the same answer. We should get the same answer. Okay. Then, so suppose if I ask you, what is the value of limit x tends to 0, 1 minus cos x by x square? If I give you this problem, then how to solve this? How to evaluate this? Okay. Again, here also I will go by the actual method, and also I will go by L-Hospital's rule. The actual method if you use, if you directly apply the limit, I am getting cos 0 here. Cos 0 is 1, 1 minus 1, numerator 0, denominator also 0. Now you know one formula, 1 minus cos x, 1 minus cos theta is equal to 2 sin square theta by 2. So 1 minus cos x, I will have to write that as 2 sin square x by 2 sin square theta by 2, so here x divided by x. Okay. So limit x tends to 0, 2 into. This is sin square x by 2. Sin square x by 2 is nothing but sin x by 2 whole square. Sin x by 2 whole square, right? Sin x by 2 whole square is there in the numerator, means in the denominator we want x by 2 whole square. Because I want to use the formula limit theta tends to 0, sin theta by theta equal to 1. That formula I want to use. So if you have sin x by 2 whole square, I want x by 2 whole square in the denominator. X by 2 whole square means x square by 4 we want. We had an x square, so but we want x square by 4. So what do? I will multiply and divide by 4. Okay. Now as x approaches 0, this can be written as sin x by 2 by x by 2 whole square. So this quantity will become 1. Right? So then you are left with 2 divided by 4, which is equal to 1 by 2. This is the actual method. Now we know L-Hospital's rule. If I directly apply the limit, I am getting 0 by 0, which is an indeterminate form. Therefore, I can use L-Hospital's rule. So differentiate. Derivative of 1 is 0. Derivative of cos x is minus sin x. Already minus is there. Minus of minus will become plus sin x. Divide by, differentiate the denominator, derivative of x square to x. As x approaches 0, sin x by x becomes 1. So we get a direct answer, 1 by 2. Okay, you can see that, you can see some steps here. Right. I'll take another example. Limit x tends to 0, root of 1 plus x minus root of 1 minus x divided by x. Okay. Now, if we directly apply the limit, what do we get? Numerator will be 1 minus 1, root 1, that is 1 minus root 1, 1 minus 1, 0. Denominator also 0. So, if we go by the actual method, we will rationalize that numerator. That is, we will multiply and divide by multiply and divide by x. Multiply and divide by root of 1. I am rationalizing this. Root of 1 plus x plus root of 1 minus x. Okay. Then that's equal to, in the numerator, it looks like a minus b into a plus b. A minus b into a plus b will give us a square minus b square. That is 1 plus x minus of 1 minus x. Divide in the denominator x into root of 1 plus x plus root of 1 minus x. Here 1 plus x minus of 1 minus x will give us 1 plus x minus 1 plus x. 1 gets cancelled. X plus x is 2x. So we get limit extends to 0, 2x divided by x into root of 1 plus x plus root of 1 minus x. X gets cancelled. So we have limit extends to 0, 2 divided by root of 1 plus x plus root of 1 minus x. Apply the limit as extends to 0. 1 plus 0 is 1, root 1 is 1. Similarly, root 1 here 1, 1 plus 1 2, 2 by 2 is equal to 1. So 1 is the answer if we go by the actual method. Now that it is in the form 0 by 0, I can use L-Hospital's rule. So L-Hospital's rule, what does it suggest? Differentiate the numerator. Derivative of root 1 plus x is 1 by 2 root 1 plus x. Minus the derivative of root 1 minus x. Root 1 minus x is, derivative of root 1 minus x is 1 by 2 root of 1 minus x into minus 1 divided by derivative of x, this one. So now if I apply the limit here as extends to 0, this will be root 1 by 2 minus into minus plus. Here this x will become 0 as I am writing extends to 0. So 1 by 2 plus 1 by 2 will get the answer as 1. Directly within one step we will get the answer as 1. This is the advantage of L-Hospital's rule. See, even in that formula also, see, I told you one formula directly, you remember I suggested. What is that? X power p minus limit extends to a, x power p minus a power p divided by x power q minus a power q. I asked you to remember this formula as p by q into a power p minus q, right? Here also I can use L-Hospital's rule, because if I directly apply the limit as extends to a, I am getting a power p minus a power p, numerator is 0. Denominator a power q minus a power q, that is also 0, 0 by 0. So I will use L-Hospital's rule. It will become p into x power p minus 1 divided by q into x power q minus 1. Apply the limit as extends to, not 0, extends to a, so we will have p by q into a power p minus 1 by a power q minus 1. So that will give you p by q into a power p minus 1. Okay? This is the answer. You can either directly remember the formula or you can use L-Hospital's rule. Or even in case of this also, say if you are not sure whether sin x by x is equal to 1 or not, that also I can get it to you by using L-Hospital's rule. Okay? So limit extends to 0, because now if I directly apply the limit, I am getting sin 0 by 0, 0 by 0. So if you use L-Hospital's rule, it will become cos x by 1. Now apply the limit cos 0 1. Is that clear? Okay. So with this I will stop today's class. In the next class we will discuss some more synopsis before we go to problems. Thank you.